Okay, it's my great honor to introduce our speaker, Dr. Robert Leamon, today. Dr. Robert Leamon is a research scientist at the University of Maryland, Baltimore County, and he also works at Heliospheric Physics Lab at NASA Goddard Space Flight Center. He has been the Living with Star discipline scientist at NASA headquarters. He received his PhD degree at the University of Delaware and undergrad education from Imperial College London. Dr. Leamon has studied space weather and sun climate for over 20 years. The overarching theme of his research has been the study of magnetic fields, from on the smallest scales of interplanetary turbulence to planetary magnetospheres and solar phenomena, including CMEs and heating the corona. His current research focuses on solar cycle evolution, geoeffective space weather prediction, and solar effects on terrestrial climate. Let's welcome Bob again. And Bob, you can try sharing your screen and start your seminar.
Okay, thank you, Ji. Thank you, everybody. Right. Do you see the big screen, or do you see the what's coming next?
Neither one.
I don't see you sharing either. Raju, I wasn't able to promote. I don't have access.
Oh, okay. I'll do the promo now.
Oh, I guess I also.
So Bob, we're not seeing you. Oh, there it comes.
Oh,
Okay. If you go full screen, will be there. We go. Looks perfect.
Looks perfect.
Yep, perfect.
Okay. So thank you all. I think perhaps the great thing about the pandemic is that it's now much easier to do these sort of presentations over Zoom. So greetings from the East Coast to the West Coast. I think it's fair to say that being at Stanford in November of 2019 was probably my last in-person interaction before lockdown number one. So I have managed to make my way to California a few times since then. My eldest is now at UC San Diego, or now over the summer, but it's just finished freshman year at UC San Diego. So I will actually be in California slightly more often than I have been over the last few years. So I'm going to talk about the solar cycle clock, the Hale cycle clock. Almost don't need to include Scott as on the title slide there as. But yeah, this is yet another Bob and Scott collaborative effort. So yeah, we're going to talk about prediction of F10.7. This is F10.7, X flares, and all sorts of other phenomena throughout the solar cycle. And really, so let's throw the throw almost a conclusion slide up first. That basically by treating the solar cycle as a clock where each individual cycle is a different length, but the cycle progresses at a constant speed within it, allows us to predict all these various phenomena. So you can see the Dali famous Dali image tucked in the bottom corner there. But yeah, imagine a wibbly wobbly, timey wimey, stretched thing that even though a cycle may last 11 years or may last almost 14 years, the progression in each cycle is constant, and we'll see that just how much this lines up across all forms of solar activity and solar output. So throw in the I've called this the circle of fifths, which we'll get to in more detail later. But for those of you who are also musically inclined, well, it's kind of a fun little add-on to talk of the circle of fifths. So I was going to say, can people mute their mics? But I will actually allow you to leave them open for a little bit, because we'll have a little fun bit of audience participation to start with. Does anyone care to throw out what those three figures have in common? There's a theme running between them. Blurt out or have Ruiji act as moderator. Anyone?
Are you talking about the solar cycle?
Well,
I mean, that's the common theme I see.
Yes.
11-year period.
Well, there is the 11-year period in the middle panel, yeah. Oh, okay. But perhaps this wasn't quite as clever as I thought it would be, or it works better in person. We'll come back to that middle panel in a minute. But the commonality between those things is me. They're all various plots from various things over the course of my
I gotcha.
of my career. But the point I want to make here is that there are different subfields of physics. We're all solar physicists, we're all plasma physicists, but we all have our different ways of plotting data and our different ways of approximations that we become two countries separated by a common language, as Mark Twain said of England and America. But they're all things of me. So I should include Mark Twain in the next coming pictures, but really everything. So we're going to talk about Terminators here. And yes, there's me a couple of years ago rocking some Arnold-esque shades. But it's not just about me or me and Scott. Really, everything we've done here is built on standing on the shoulders of those who have come before us. So I guess David Hilbert there on the left bears a bit of a resemblance to Mark Twain and two countries separated by a common language. Hale, of course, is the reason why we're here. And we'll also rely quite heavily on the gentleman on the left, who is Charles Tree, who is the inventor of the superposed epoch analysis. We'll get to him. And the other gentleman there is Rossby, which we may or may not get to Rossby and his eponymous waves. But then we've already mentioned Dali already, but so these three gentlemen share a birthday, and I've always felt a certain affinity to both of them, just because they do share my birthday, or I share their birthday. And of course, we've already mentioned the persistence of memory and the stretchiness of time. And a lot of this work, the inspiration came from me doing training for an Ironman and a few years ago. And if you look at lap data as a function of distance, obviously, if you go around a distance, then it's the same distance each time. But if you do it as a function of time, you might be faster or slower. And so by looking at my own power data, if you look at it as a function of distance, every time you come to a hill, your speed goes down and your power goes up trying to climb up a hill, which you might not see if you try to do a superposed epoch analysis in the way of time. And Feynman, of course, is fun and cool, but it's not really Dick that I want to talk about. It's more it's Sister Joan, who passed away a couple of years ago. But she actually did work on the solar cycle. In fact, still one of the best proxy predictors of how strong the solar cycle will be is the AA index at minimum that she promulgated in mid to late 80s, and we'll come back to her as well. So, but also really the other great thing about Joan is that swords are cool, and my kid also fences, so we're going to throw this one in here as well. So we're going to talk about terminators, and so what I mean by a terminator is when there's no more old cycle flux left on the disk. It is all cancelled, it has all died out, it has all been terminated at the equator, and it really is quite a sharp transition from one cycle to the next. So this is the bright points, the small scale magnetic elements distributed all across the disk, and they form a somewhat extended butterfly diagram, just like the sunspots. In fact, if you were to overlay this on sunspots, the red area, especially from 2011 to 2016, is when we had significant sunspot activity on the disk in the last cycle. But then also notice that at minimum, especially the deep dark minimum from 8, 9, 10, there's actually there may not be large scale magnetic elements, no sunspots, but there is small scale distributed all across the disk, and you can see the clear delineation between the old cycle and the new cycle there at the beginning of 2011. So there's the turning off of those small scale magnetic elements at the equator. The rapid, less than 27 days on off, is what we mean by a terminator, and like Arnold, they will, as always, be back. So everyone likes to predict how strong the cycle is going to be in terms of sunspots, but I almost like to think of F10.7 as my preferred scalar quantity, because it's actually the longest running physical solar observation we have. Watts per meter squared per hertz, going all the way back to 1947. So I'm slowly going to fade out between the Penticton F10.7 value and the underlying elements. You can see just where we have the activity. Not surprisingly, the core of the cycle is where we have the activity, and this F10.7 equals 90 appears to be something of a magic number when we have strong activity on this, and we'll keep coming back to this throughout the talk. So I guess I kind of introduced this slide already, but we're looking at those small scale magnetic elements, and if you track the let's actually flip back a couple of slides, that you can actually fit a line to each of these, and if you play with the color table or choose a different color table or scaling, you can actually see the new cycle forming at around or just after the maximum of the previous cycle, and then you can fit a fairly decent linear fit to the equatorward progression of this. So that's a slightly old photo. Let's update it slightly. There's with sunspots as well. So there's sunspots already on the disk coming out of minimum, but the terminator happens a year or two after the canonical sunspot minimum, and I'm going to argue that is the key time. So don't think of a solar cycle's fiducial clock running from min to min. think of it instead when reset your lap counter when there's no more old cycle flux left on the disk. And the other thing that you see here is that these things are almost non-existent above about 55 degrees. There's 55 degrees is somehow a very fundamental latitude with different dynamics or magnetic behavior, motions and flows above and below. I mean, both above and below in terms of latitude and in terms of depth. So this is a very colorful eye chart. This is the Pat McIntosh archive going back from 1960 something to about 2010. You see the right, yeah, to 2009 on this, but you'll see that where so the terminators are in pink here. And there's the underlying red and blue cartoon of those bands. Of course, you have red and blue because each cycle alternates polarity. But you see that when the terminator happens is when you start to see the rush to the pole of the highest latitude filaments, which is in green here. So the 55 degrees is marked. It kind of hangs out. It never gets above 55 degrees until you get to the terminator. Look at 1988 in the middle of the plot there, and then it jumps up, and the reversal happens a year or two afterwards at close to sunspot max, and then the next polar crown filament reforms again back at about 55 degrees, and we'll come back to filaments again. So the termination at the equator kickstarts the growth of mid-latitude sunspots, and then the rush to the poles of filaments that were hanging out at about 55 degrees. And this is all very rapid and in sync with one another. So that says something about the flow of information inside the sun and places some limits on the magnetic fields that must be existing subsurface. And the other thing that we see happens with at the terminals, you know, with the surge of sunspots and the surge of activity is that we have X flares. So again, there's a lot going on in this plot. So you can see that the sunspot number, and rather than doing it by month or smooth, this is the daily data smoothed by 3 rotations. As you can see, it's quite surgy back and forth. And then on top is that butterfly diagram of bright points again. And then the red and blue dots are the occurrences of X flares, in red being north and blue being south. And the bottom panel with the lollipops is the size of the lollipop is the size of an X flare, and it's color coded by latitude. You can see just all the large amount of activity at Halloween in 2003. The biggest circles, and then just how quiet cycle 24 was compared to cycle 23, and now we've had a few X flares in 21 and 22, right at you know, coming from December 2021. So we have this coherence of all these things happen simultaneously in, on, and over the sun. Talked about a whole bunch of different data. We're going to bring in one more set of data now. Let's use Stanford Wilcox. So what we're going to see for the next few slides is that I'm going to present you some time series data. So here's the dipole, quadrupole, and octopole moment. again, the terminators are shown by the thicker dashed lines, 1998 here, 2011. And you can see obviously there's not much. The biggest change you see here is in the quadrupole projection, and then the dashed lines, the dotted lines are 3/5 of the way through the cycle from one to the next, which concept of, so we've been calling it the pre-terminator, based on Sandra Chapman. As a first author paper with Scott and myself and a couple of others from 2020 in GRL, that there's a change in the AA index and in the number of X flares at this point. So we're going to keep coming back to it, this 3/5, and then we'll introduce the other ones as well. So again, don't think of this as, you know, as a time series. What I'm going to do is now I'm going to break it down into a superposed epoch analysis and do that Dali-esque thing, and stretching and compressing the time between each dashed lines on this into 0 to 1. So here we go. This was, you know, modification of tree here. So the striking thing here is then look at the polar field strength at the bottom there, that the revert, also on this scale of 0 to 1 being the terminators at the equator, that the polar field reversal happens at 1/5 of the way through, and that's, you know, all four cycles that we have for Wilcox. And so we'll see how this pans out in 2024, but I'm quite confident here. So you see the reference we've done here is T for terminator, R for reversal, PT, which is a bit of a clunky name. Still need to think of a better one for it, as this 3/5, and then little m for minimum. So let's do the same thing now for F10.7, goes flares, and then as coronal, as a measure of the corona, the green line, and then an EIT and calcium K in the chromosphere. So on the left of this figure, again, we've got in time, and the right is in this scaled cycle length. So so the top panel is at the trace is F10.7, and then all the red dots are all the X flares, goes X flares. So there's 453 red dots on that panel because they cluster, of course. The second panel is the green line intensity from Czechoslovakia primarily, but it's the global source. So to take the annulus off the limb and measure the intensity in that ion line, and you see the progression. You know, so essentially, it's the butterfly diagram, the progression of activity. You see the rush to the pole, and the fact that you've got the two bands, the new cycle and the old cycle, existing on the disk simultaneously. The third panel is the polar field strength, again, that we showed on the previous one. So even though we had that very long, unusual minimum cycle 24, if you stretch it accordingly, they all line up at polar field reversal at 0.2, and then if you look at the calcium K in the bottom right, I didn't put the calcium K as a straight time series, but you see that the upper latitudes, because you lose the coronal hole, it goes polar coronal hole. It goes dark at high latitudes from about 0 to about 0.4 when it reforms, and you see clearly that the termination of at 1. So I think I've kind of said half of the text of this already. So let's see, there's 453 red dots on that plot, and there's only 12 of them that happen outside of this zero, the first 3/5 of a cycle as measured from the terminator. And I cannot stress this enough, that on the clock that goes from little bright points at the equator, the polar field reversal always happens at the same phase.
Bob,
Yeah.
This is live. I have a problem with the top panel. If you were to plot with red dots the month in which there was a murder in Chicago, you will get exactly the same figure. So it's somewhat.
If I were to plot the red dot, the red dots, what? Sorry.
Well, on the top panel of 10.7 and X flares, the way you plotted it is a little bit deceptive, I think, because if you were, as I said, to plot with red dots the month in which there was a murder in Chicago, and there's one in every month, you will get more or less the same plot. So I don't think you should plot you shouldn't plot the red dots on top of the F10.7. That's
valid.
Pushing it, I think.
Valid point. And we'll actually come back to X flares in a little bit. I think there was I think that the rationale of this was early on in doing this work. We see that the X flares tended to be looking at a not so much the base level of F10.7, but how much it had surged recently. But yeah, we can talk about that more later. So
okay.
So yeah, so I'm just going to stick with F10.7 for the next couple of slides. Then so you can see there's five traces just plotted on that graph, but let's actually make them as make a unit cycle of F10.7. So this is the full record going back to 1947. And take F10.7 equals 90, and the rate of change of sunspot number as defining the terminators back when we don't have disk resolved magnetic images. So each of those 7 cycles, I'm going to split into 100 time steps between terminator and terminator, and then compute the average and standard deviation of each cycle, but scaled to the maximum. So you can see that the cycle 24 here and 20 were quite weak. 19 obviously was the biggest of the space age. Yeah, so you see that the bottom panel here is scaled to a peak of 1. So each of the red, the black curve here is the average cycle, starts off at 90, but scale down here, peaks just after reversal. So you see that there's a dip around polar field reversal, so that there's actually less magnetic activity overall on the disk. You can really think of F10.7 as a measure of global magnetic field complexity. And so at about 0.4 then, when, remember we said, we talked about the polar coronal hole and polar crown filament reforming after reversal, to this sharp drop in activities was really noticeable in 1971 there, or most noticeable, but it happens across all the cycles, and then decays back down, continues to decay down till you get to 0.6 cycles, when it reaches that same level of about 90 flux units. So really, this is so you need to have F10.7 above 90 when we have an active enough corona to want to generate X flares. And then just to complete the cycle, then we have canonical minimum is at about 0.8 of a cycle. So there really seems to be things happening at these landmarks of 1/5 of the way through the cycle. So talk about Eve on SDO for a second. So obviously this is only one cycle. So on the leftmost panel here is it's Eve. This is Eve lines, but it's the Eve lines that correspond to the AIA filters, and I've put them in the appropriate colors for the JSOC output as well. So each of those lines, I scale the average to the 6 months before this terminator event in February 2011, and then each of them is shifted up by 1. Other than the very last one, the 94 line is shifted up by 2, just to account for the fact that the 335 below it is the most active. So all of these things, turn on suddenly and rapidly and simultaneously at this energized corona level. And then the right hand side obviously has less data because of the Megsby anomaly, but that 335 again shows it. There's like a factor of 2 drop in the course of less than a rotation. You can see the dashed and dotted lines in mid 2016 are 1 rotation apart. So that's the left hand pair of images is just the AIA lines. The purple haze, the Spinosaurus, whatever you want to call it, on the top right is all the Eve lines. You can kind of see where some of them fail in mid 2014 there, but all the lines turn on simultaneously in 2011, and they all turn off simultaneously in late 2016. The black trait at the bottom is F10.7, just to for comparison with the person, and that dashed line is 90. So when you have your terminator, there's now a freedom to increase the magnetic energy flowing into the corona, which leads to a hot corona and all this EUV emission, and the F10.7 from the magnetic field and the X flares. Yes, a little wavelet transfer. You can see the 27-day periodicity when you've got active regions on the disk, and then in 2016, that's when they go away. Right. So we get into a bit now about how we see this throughout the heliosphere. This is not just a flaring phenomenon. It's not just a photospheric phenomenon. It is pervasive throughout everything. So here's kind of like the green line plot that I showed before of the 195, 193 intensity as a function of latitude. So to take an annulus off the east limb and measure the intensity as a function of position angle, it is smoothed a bit and then plotted over the whole mission up to I think mid May is when this up. So you see, and then F 10.7 again plotted at the bottom. Is either when you've got this F 10.7 is above 90 is when you have emission above 55 degrees, and we have the quiet. Once you get into minimum, there is no activity above 55 degrees. So even though we're looking at sunspots are limited to a very narrow range. At this point, they're only down to 10 or 15 degrees latitude. There is a dearth of activity of any sort above 55 degrees. So I said going through the heliosphere. So this is Omni data going all the way back to 1960. I cut this off so that to 1972 or 71. So from the top, we've got the mean magnetic field, density, solar wind velocity, the fraction of alphas of helium, and then again F 10.7 at the bottom, and I've drawn the green lines of the terminators and the red lines of those 0.4 edges, the Devil's Tower drop off. And you can see that in the top panel, the peak mean field of the IMF peaks at this 0.4 and then drops off as we get down to minimum. And again, the alpha particles, the most helium in the solar wind peaks or is at least elevated from the terminator through activity maximum, and then drops off quite sharply. So again, this is all at 1 AU in the ecliptic, but we'll move out. I think this actually is a fun thought. So we actually break the helium. The previous slide showed the helium across all speed bins, and here it is broken out into 4 different bins of speed, down to the purple to the slowest, to the red of being fast solar wind, and the solar cycle modulation of helium across all is the biggest change happens in the slow wind. The fast wind is much more limited dynamic range, but they all follow it and they all peak at around 0.4 cycles. Excuse me a second. Right, so that's at 1 AU, but actually now we're going to get out of the ecliptic. So this is really fun. So we're all used to thinking about SOHO being home to LASCO and EIT. We forget about the other instruments. And yes, we've used and MDI of course, but there was actually a whole bunch of other things. So this is from the SWAN instrument that actually is an outward looking Leamon alpha camera, sorry, and as the spacecraft moves around the sun, it can see more of the the outer. So this is so the top panel is the mass flux of protons coming into the or the neutral hydrogen streams in from outside, undergoes charge exchange. This is what IBEX and IMAP see, of course, and so now slow moving, relatively neutral hydrogen back scatters the solar radiation, so it actually sees as a zodiacal glow almost of Leamon alpha, looking outwards, and you see that, you know, when we have activity on the disk, you see this throughout at all latitudes in the heliosphere, and then, you know, when we get to that 0.6 level, it falls away again, and this is kind of cool time. So this is just related to Parker Solar Probe. Obviously, this is not Parker data. This is wind data that Justin used to calculate based on the thermal properties of the plasma you observe at 1 AU. You can figure out when it stopped being heated. Where is the alphane critical point below it? I don't know if how clearly you can see the red line on this curve, the sunspot number, but you can see that there's clear discontinuities in 98, 2003, 2011, 2016 in the average here. And if we throw on those lines, then yes, we are not supposed to see that as the alpha, the distance of the standoff distance of the alphane critical surface is predictable. Obviously, you know, it's not a perfect sphere, of course, but we can say something about its activity and what's it going to do, and based on this, and knowing the Parker Solar Probe trajectory, we said, you know, it's going to be in, you know, last 6 months of 2021, we should fall below this, and well, more or less right in time. So the April 21 was when they Parker first encountered subalphanic solar wind. So I think that's pretty cool. So right, to see, we're at 2:45 already. So we'll talk about the motions of filaments and the landmarks of the cycle here. So this is perhaps an inverted way of showing that. This is actually plotted as a function of cos latitude rather than sine latitude. But I like this because you can see more clearly each cycle's progression and the overlap between the two. So here's you can clearly see filaments tend to live in two bands on the disk, the current cycle activity band, and then what will be the next cycle activity band that hangs out at higher latitudes, and starts creeping down. So here we've plotted it as a function of latitude, you know, North Pole to South Pole. What we do now is the next plot is going to flip that to be the absolute magnitude of the latitude, and X's and O's correspond to the north and south hemisphere. Again, you can clearly see. So if we look here at after the terminator, we see there's nothing before 0 or 0.6, 0.8, 0.1. There are no or almost no filaments above 55 degrees. They immediately start rushing polewards at the terminator at 0, and then 0.4 they seem to drop off below about 75 degrees, and then at 0.6 there's nothing below 55 degrees. I should point out that if you see that this is all very banded, so the Meudon and before that the Arcetri archives only quantized their data to 5 degrees. So we've kept that here. Again, it's just 140 years of data, 10 plus cycles, and they all follow this same pattern. So we'll come back to the 75. So 55 we understand. We'll come back to the significance of 75 in a minute. I just want to touch on, so Leif commented before about X flares and months with X flares in them. But I think this is something fascinating. So how does the sun know which way is up? That is, there is a difference between many forms of solar activity between odd and even cycles. Now, sure, we don't think that the cosmic rays, depending on the North Pole polarity, then cosmic rays either stream into the inner heliosphere down from the pole and out or in from the outer heliosphere. So, but that's well understood. But even in terms of things like flare rates here, so the odd cycles, the white and green traces, is a fairly steady run of X flares all the way out from 0 to 0.6 when we've said there's no more X flares. But the even cycles tend to be done by that 0.4 polar crown filament reforming stage. So even though there's so this is a work in progress, and of course cycle 24 being quite a weak cycle has something to say. But the little inset here is from a paper by Matt Owens from last year, argues that the most geo-effective storms happen when the global corona is well, the north pole of the sun is north, which either happens then in the declining phase of odd cycles, or in the rise phase of even cycles. So cycle 25 is well odd. So we can make predictions then about what we're going to see in terms of X flares. We're going to continue to see X flare production through mid 2027. So if you just take 11 and a quarter years and tag it on to December 2021, then 6/10 of a cycle is mid 2027. Incidentally, it's going to be almost exactly the same time as orbiter is going to get up there, and so we might expect then, given it's an odd cycle, it's going to be G-effective after max. So think Halloween rather than Carrington. So 24 to 27, better make sure your power grids are well installed. So yes, so not directly relevant to terminators, but you know, we'll skip. There's interesting things about just how fast flares redo, and so the HCS current sheet tilt from Wilcox here in white. There's also a clear difference between odd and even cycles, and that the green dashed line here. So it seems that like 23.4 degrees, so the Earth's actual tilt is a good approximation of the terminator. I think that's just numerical coincidence. But it is that there's one more thing that odd and even are different. So we'll skip magnesium. And so somebody asked me the last time I gave a talk at the source meetings later, how can you explain why we have the sudden turn off and turn on of coronal activity? You know, because it happens that, you know, at you know, that this 0.6 of a cycle is when the old cycle bands are at about plus or minus 15 degrees. So is it that they're now close enough to interact and start canceling each other out, which means that there's less free energy to get into the corona and heat it up? Or alternatively, is the differential rotation profile at about 15 degrees means that it gets too sheared to form active regions. So I know Masumi Dikpati is doing some simulations that might favor the first version of that, but we'll watch this space, and yeah, we'll know that we say that we're going to see a more active cycle just because of, if you do how far apart terminators are, this nice linear relationship. So we'll skip the F10.7. There's anything else? So, so again, the torsional oscillation is part of this as well. The terminators is when we see the flip of torsional oscillation, polarity, if you will, sense of the torsional oscillation at the equator. But really, it's because the torsional oscillation, it is a magnetic phenomenon. So yeah, so these are my thoughts. It would be remiss of me not to include Alison Liu's version of this, that the extended solar cycle, the Hale cycle, is the cycle. And we'll skip that. So yes, if you have one take home from my talk today, I mean, I'd like you to appreciate the Hale cycle, but really, please, the #1 recommendation for any of you who are involved in the decadal survey, it absolutely has to be a 4π mission. Stereo doesn't cut it. You've got to visualize the whole sun, all the, you know, SDO's, the motto was all the sun all the time. It's really just continuous data all the time. You want to visualize, treat the sun as a meteorological object, because you do have things like Rossby waves in it, and to get above the poles to see what's going on above 55 degrees is key to understanding, it is the key to understanding the dynamo. So to wrap up then, the solar cycle can be viewed as a circle of fifths. The two overlapping Hale cycles lead to this fifths pattern of polar field reversal at point 2. The PCH and polar coronal hole, polar crown femoral reform at high latitudes at 4/5, 4/10 of a cycle, 2/5 of a cycle. You get no more X flares and change in X flares and storms and A index at 0.6. We've got the filaments play a role throughout the heliosphere, and when will leave us then with knowing how long the next cycle is going to be, and that relationship of how strong a cycle is and how short the next one is. We can take that average cycle and make a prediction for the next 11 years. So that what I've previously showed you in red hash marks is now green in this plot. There's the NOAA historical tracking, and then the observed in red, and we are tracking extremely well and much better than the NASA prediction panel in the red curve. So summary then, if you take this Hale cycle interaction bands and it moves at a constant velocity within each cycle, we can make predictions about what F10.7 is going to be, what flares we're going to see, what the spectral irradiance is going to do, so implications for drag and weather and climate. And so, since this is COFFIES, whatever models we run must be able to match data, and that includes what goes on at the poles, how we get the interaction between systems, and keeping those filaments at 55. And I say, what was the significance of the 75 filaments at 4/10? Well, if you take the rotation frequency, so it's constant at depth at about 55 for most of the most of the convection zone, but then the little surface blip here at 75, so that might have something to do with it. Yes, there's our prediction again. So in summary then, the Hale cycle terminator is the key time, not minimum. We've made some bold predictions for the next 11 plus years, including a max of about 190 in mid-2024. And we will monitor the sun's experiment while figuring out the how. So everything is predictable with cycle phase. And I'll say thank you very much, Diolch yn fawr, and field any questions you may have.
Hi, can you hear me?
Yes, I will stop sharing. Where's Chrome gone? Okay, who was asking a question? Although Nick, I love your Bob Ross there.
It was me, Alan Title.
Oh, hey, Alan.
Hi.
Yeah,
First
sorry,
of all,
I totally failed to give you credit. I did in my notes and I didn't say anything with regards to the occurrence rates, the flare rates there. So anyway.
So first of all, I agree with you completely that we're missing something very fundamental when we don't look at the whole sun. And that, well, first of all, your remarks on X flares, that 93% of the X flares occur in something like 6% of the time. And this clustering is about 5 standard deviations from what you would expect if they just occurred at random. And that all flares down through C all cluster. The spacing between the fraction of the time that you're in clusters and between clusters, that number is, as I said, a factor of nearly 20 or a little bit more than 20 for X flares, but it drops down as you go from below 10 down to C. But in any case, that something else is going on that we have evidence of from these things called nests. But again, we have to learn something more about the whole system. We have to make dynamo models. Dynamo models have, I'm lecturing, dynamo models have been not pursued very much in the past decade, maybe a decade and a half, because we really don't have any experimental evidence that can validate the models. And until recently, you couldn't take them to the surface. But we're now approaching the time where we can do that, or at least make a real attempt. And so that going along with this 4 pi tack, we really ought to encourage a resurgence of dynamo models using the biggest computers that you can get, because that'll turn out to be very important for all of astrophysics. And the sun will be a system where you can verify that. Anyway, are your slides all available? Can you send them to me?
I will send them to you, and I can make them available to the group as well, to Coffees. I'll talk with Riju and Todd offline. But yes, I will definitely make these available.
Has Scott shared with you this draft of my Nature article about clustering?
He did, yes, and that's what prompted me to throw in those throw in the flares bit, which you inspired me to play with. Where's my presentation gone? Yeah, so we do the. I mean, I love your quote of the best predictor of an X flare is an X flare. Yes, I did say title. That yes, we do the how long it's been since the last one. There appears to be this 4 or 5 rotation limit that something comes around again. So, and then about 12 hours seems to be the edge on the other side. So yeah, there is definite clustering going on. And yes, I will.
If you're in,
Okay.
if you're in town maybe it would be a really good idea for you and I and Leaf to get together and look at how our different perspectives of some of these things merge together. I think we're all pounding on the corners of the same box.
I think that is probably true, sir. Yes. So yeah, I will let you know the next time I am in California with tea, and maybe I can pop up before or after.
Okay.
Could I ask a question? David Hathaway here.
Hey, David.
Yeah, hi. Couple of things. First of all, it's not really a Hale cycle clock because it's not 22 years long. So it's really a solar cycle clock. Secondly, you don't know the rate at which the clock runs until the next terminator. So you don't know what phase you are in cycle 25 until the end of cycle 25. I would like to point out that I wrote an article in 2011 in Solar Physics about a standard law for the equatorward drift of the active latitudes, and noted there that, yeah, minimum is not a good time because it depends upon the previous cycle. Maximum's not a good time because it's different depending upon the size of the cycle. What I found was that if you fit the beginning of a cycle to a function, and a cubic works for the very beginning, that starting time is a really good indicator, and it comes at the beginning of a cycle. And given that starting time, every cycle, regardless of size, regardless of even, odd, or anything else, follows the sunspot latitudes follow the same path down towards the equator, with a clock running on the clock on your wall. So just like to point out those aspects.
Yeah, I think you're right, of course, that I don't truly know the phase until it's done. But so any of the projection stuff I made as just assumes a 11.25 year average. But if I say that polar field reversal happens at 1/5 of a cycle, then when the polar field does reverse, which I'm currently estimating for mid-2024, then I can just multiply that by 5 and say, okay, before I said late 2031, it's in fact going to be mid-2032 or 33 or whatever. So yes, you're right about. I can't strictly predict the phase, or even now I've got to wait 2 years to confirm it. But yeah, I think I was aware of that paper, but I'll definitely go back and give it another read.
Yeah, both of you, there's a problem that the polar fields reverse at different times in different hemispheres. So this is not a one-time thing. Huh? It's maybe up to a year difference. So,
but I think what I've plotted there has been the average, the standard product or one of the standard products that Todd puts on the website every rotation is the north-south, the smoothed, and the average. So yes, they are a little out of whack, and certainly they were in 2011, 12, 13, but their average does follow this rule tightly.
and since they reverse at different times, one may wonder if the terminators are also different in the two hemispheres.
I'm going to say, well, no, because it's an equatorial phenomenon. So it is the cancellation of the two. Now
That may
Certainly.
that may happen at different times, just south and north of the equator. That's just something to keep in mind.
Yeah, you're getting a little ahead of me even there. So I do see three more hands up.
Okay.
And there's also a question in chat. Let's follow the time order. I think Janet in the chat asked question first, and then Todd, and then Robert, and then Gregory. Okay. Janet, you want to?
Sure, I can say it best. It's great stuff, Bob. I really enjoy your talk. One question I always have is the use of sunspot number for so much, for defining phases and milestones within the cycle. You know, we all know that sunspots are a really imperfect measure of the solar field, and yet they're widely used for this purpose. If you've pointed out that 10.7, F10.7 might be superior in some ways because it has some element of non-spot fields in it. So I wondered if you elected to define some of your markers in terms of F10.7 rather than sunspot number, would your results change at all, or would your thinking change at all? Because then you would be including the active region, spotless active region.
Sure. So it really does fall. So, from 1947 on, which is when we have F10.7, it really only is a month or so's difference between that F10.7 equals 90 measure and then taking the Hilbert transform of the sunspot number, which is how we've pushed the timing back to 17 whatever to come up with that linear relation of strength, cycle strength, and cycle length. So yeah, I'm fairly confident that F10 is a decent a very good scalar proxy, and I have not yet done so, but certainly I could push that green that green curve I showed in the last plot or two and take that all the way back to 17 whatever and make make other approximations, the likes of things that Matt Owens and Lockwood sort of thing like to do with historical data.
Thanks.
Todd?
Thanks, Bob. Nice talk. As always, lots of interesting things to think about. A couple of my questions were already answered. One was about how soon you could determine what phase you're at, or what the length of the clock is going to be for a given cycle. And we already talked a little bit about the time of polar field reversal as being one of your second markers after the termination. And as also was mentioned, the reversal in one hemisphere this last time was pretty extended, and the other one was pretty sharp. And other cycles have had the same thing, where there's a difference between north and south, and certainly you can average them, and maybe that's the answer, because that's kind of what you found. I guess the more fundamental question, this maybe calls for a little speculation on your part, and maybe it's something that in COFFIES we can answer in 5 years, is why do the clocks for one cycle differ from the clock for another cycle? Why is one longer? Why is one shorter? Do you have any insight or any thoughts on why that might be?
Sure, and as you say, this might involve a little bit of speculation on my part, but for whatever reason, actually, let's where is the bad? was. Sure. So let's go back to this figure. So what? So look at the second, for the green line figure, that's the second panel at say 1992, 3, 4. So what's going to become cycle 24 appears at about 55 degrees, just after the maximum of the previous cycle. So whatever shearing dynamo properties, I guess the best way to describe it is, think of like, the wave machine in the kiddie pool, that for whatever reason, some amount of flux gets sucked up from the tachocline at 55 degrees and raises up into the convection zone, and then there's got to be a physics 200 level level calculation of Biot-Savart or something, that if you've got or maybe Nick Featherson, if he's still on, can give me an answer to this. But if you've got these two systems, one at plus 55 and one at minus 55, with so much flux in them, then they're going to be attracted to one another, and how would they, what would be the net force on them and net acceleration, and how would they drift towards the equator? So maybe it's just I'm going to scoop up so much flux that is then going to propagate equatorwards. And then the other thing was, is why does a long cycle give rise to a weak future cycle? I think that's but the longer that those systems are on disk, remember that they're of opposite polarity, so there's more opportunity to interact between old cycle and new cycle, especially if you think about delta spots and biggest flares happening on the outer rims of the activity band. That essentially, you're eating away at the next cycle flux, so there's less of it to give rise to the next cycle. Does that answer the question good enough for now?
Okay.
I think as well as it can be answered. Thanks, Bob.
Yeah, that requires millions of hours of CPU time and millions of dollars of thought, but we must try.
And we still have 3 hands raised. Robert, are you still?
Yes. So I just want to go back to Dave Hathaway's point and note that not only do all cycles follow the same trajectory in latitude as the cycle progresses, they also have the same cycle amplitude in terms of sunspot number. They have the same half width of the butterfly diagram, and all these match and are the same from cycle to cycle, weak cycle, strong cycle. And this goes back to Waldmeyer and Dave Hathaway's paper in 2011 and Manfred and my work in 2016. And I don't see how all cycles can behave the same way if we're stretching time. And I don't see how all the cycles can behave in the same way in the decay phase if there's strong interaction between the two cycles. So do you have any idea how to reconcile that all cycles decay in the same way with this idea of interaction between the two bands?
I think I have to say the the width of the butterfly diagram is perhaps not really what you want to be looking for, because if I'm just weakening the flux system as a whole, the hand waving argument that I just tried to give to Todd, that there's no reason why, you know, any individual element that, you know, if it has a certain amount of magnetic flux and a certain amount of buoyancy, then you're going to get a flux rope to rise up and then spread apart and become sunspots and a twisted corona above it. But I don't think that.
But it turns out the observations show that the properties of the cycles, all the properties we can measure, are the same in the decay phase of the cycle. So the width of the butterfly diagram, the number of spots, the tilt angle of those spots, the latitude at which they appear. So you take this very simple timing from the latitude, and then all the properties of the cycles are the same in the decay phase. And I'm not sure how to make this consistent with your idea of either stretching time or consistent with your idea of the bands interacting.
I hear you, and I think let's see what happens between now and 2027.
Okay.
Okay, Greg.
Thank you. Very interesting talk. Just on the point of the turn on, I just wonder if there are two processes going on, like a surface dynamo that's a constant, a steady phase thing that's just there, and a variable one, a deep dynamo or whatever. And if you had those going on, could the turn on be the emergence or the exceeding of the time of where the large scale dynamo exceeds the intensity of the of some kind of surface dynamo or a constant dynamo, which is constantly generating brightness or response in these various ways?
Yeah, maybe. I mean, I am certainly not a dynamo type, and while I'm aware of the concept of surface dynamos and people modeling it, yeah, I guess you could say that there is some threshold to be breached, and once you do breach that threshold, or the dam breaks, if you will, then there will be a sudden influx of activity. I know Masumi has modeled us, you know, as a tsunami, shallow water tsunami at the Taka climate. You've got the old cycle flux that kind of acts as the barrier, and once that breaks, then there's a wave, an alphane wave or a magnetic wave of sorts propagates equatorwards, propagates polewards, and you know, if you say it's an alphane wave, then you can say something about how strong the field must be if there's a time gap between what you see at low latitudes and mid latitudes, and I think that turns out to be quite a large field, in fact.
Well, I was more. I'm sorry, but I was more thinking of just observationally, in terms of a floor to the emission that is always there, and you could imagine you extending a trajectory that goes down below that for this separate process, so that you don't have a turn on so much as a a continuous trajectory, same slope, but now rising above this constant floor. That was just more of an observation.
Okay, yeah, I see, because that there's three components to F10.7. One is thermal. Basically, you've got a chromosphere at this temperature and a corona at that temperature above it, and black body says you're going to get about 60, 65 SFU, and then it's the Bremsstrahlung and synchrotron gyroresonance components that are tied to the complexity of the magnetic fields in active regions that generates the big turn on, and then the spikiness, the activity in the core of the cycle. But yeah, I certainly could say that you've got a yes, you could model it as a base threshold and something that waxes and wanes above it, sure.
Okay, last question, live.
Yeah, I have two short comments. Let me share my screen. This will stop. Yes. Okay. All right. First comment is, it is often said that the sunspot number is a poor measure of activity. To me, that is usually just an excuse for why is it that the sunspot number does not agree with my theory, right? So if one defines activity as the magnetic flux on the sun, then you can see that, that the group sunspot number, that is the number basically of active regions on the disk, is a very, very close relation to the total magnetic flux. At the bottom of this plot, I show the magnetic flux derived from HMI and MDI and Wilson and Wilcox. They're all normalized to HMI, and you see they agree very nicely. And on top here is the magnetic flux as a function of the number of active regions on the disk. And that's a very, very nice and tight relationship there. Interestingly enough, it doesn't go to zero when there's no spots on the disk. So that's a different issue. Some of that offset is probably due to noise in the magnetic field. So it's probably not quite that large, but let's say half. So the sunspot number and the group number is a very good measure of magnetic flux on the sun, and is therefore a very good measure of solar activity. That's number one. Number two. Number two is something I think, first of all, I want to comment that is very brave of Robert here and Scott to propose this new order of things. And show another screen. Share my screen. My problem here is, of course, I have 7 screens. 7 is a quote by Nicola Machiavelli, and it says, if I can find it, I don't want to look for it now. Basically, it says that there's nothing more difficult than to introduce a new order of things, and that is what you guys are trying to do, and that is hard. It's brave of you to do it. So let's hope that future will be kind to you. Let us see. So very nice talk. Thank you.
Thank you. Yeah, let's see. It is hard to change a man's mind if his salary depends on not understanding it, or I'm butchering the Upton Sinclair, The Jungle, but yeah, same sentiment, and I know what you mean by Machiavelli. Yes.
Yeah.
Okay, we are we are heavily over time today, but I think we all have a great talk from Bob, and we all have a great discussion. Thank you all of your time, and especially to our speaker Bob, a very nice talk.